All right. Okay. So off we go on EE308 topics. Okay. So far we've figured out where the R's are, where the C's are, and figured out how they create a pole. And then we use small signal analysis to find a zero. And that was all. If you just use the op amp, that single op amp, that's how we found the characteristics, the frequency response characteristics. And if you have a corner and you try to give a signal that's a higher frequency than that corner, then it gets attenuated. So that's where we are so far. And then now we're going to look at feedback. And I'm trying to figure out which one of these whether to skip Barkhausens. We talked about it at the end, but let's just look at feedback in general. We'll come back to Barkhausens in a second. So feedback in general. If you have, remember our underlying op amp. Our underlying op amp might have a corner frequency here. If it's a 3-stage op amp, so it has an input stage, a gain stage, and an output stage. That means between the input stage and the gain stage, there's a pole. In between the gain stage and the output stage, there's a pole. So it's a 2-pole system, but let's say the second pole is far enough out that we can kind of ignore it a little bit. So we're just treating this as a single pole system for a second. And you have something like this. So in this system, if you hook this up with feedback, what happens is that the gain drops by a certain amount. So this feedback factor right here, it keeps the gain from being as big as your underlying op amp's gain is. So if your underlying op amp's gain is AV, then the feedback factor will make your gain from V in to V out less than AV. It never increases the gain, it always decreases the gain. And what's interesting here is this magnitude, again, it's 20 log, should lift myself a little more space, of gain, absolute value of gain. This point right here is actually your underlying, so this, let me write this. This is 20 log of AV. So it's just your underlying op amp right here. This is actually 20 log of AV divided by 1 plus AVF. So whatever the gain of your op amp is, it's divided by 1 plus the gain of your op amp times your feedback factor. And you've seen non-inverting op amps. We'll see, we'll work on figuring out exactly what F is here, but you can see that the voltage at this node is V out. Since there's no current going into the inverting input, this just works like a voltage divider of V out. So the voltage at V in minus equals your R2 over R1 plus R2 times your V out. So it actually decreases V out and feeds it back. Okay. We'll go into a little more detail there, but you can see that however much V out moves, the voltage at V in minus moves less than that, because V out is being divided. Okay, so this new, the once you add feedback, your gain drops. But you can imagine if this circuit right here, if your underlying amplifier can't go faster than a certain frequency, then there's no way when you add feedback that the amplifier will magically start to be able to work at a higher frequency. So your underlying op-amp has that limitation. It can only work at up to a certain frequency. So what happens is when you drop the gain, when you add feedback to this, it comes out, and as soon as it hits the line here for your underlying op-amp, it starts to follow it down. And that makes sense, because if your underlying op-amp can't work at a higher frequency than this point, then even when you hook it up with feedback, your underlying op-amp can't operate at a higher frequency than that point. Okay. And this has a special name. Notice when you drop the gain, the frequency that you have a constant gain at now moved this way. So do you remember what this is called right here, this value? Where it has a flat gain, where the gain's pretty constant?
DC gain?
You say it again?
Is that DC gain?
It is, but how about this frequency range right here?
Is that the gain bandwidth?
It's part of that. It's the bandwidth. So the flat part up top, I really should have left some space up top. This from here to here, you'd say that is the bandwidth of your underlying op-amp. That's the range of frequencies where you have a constant gain. Is that okay?
I thought bandwidth is to the -3 dB point. Or is that different?
Yeah, I'm kind of sketching it here. So.
Oh, okay.
Yeah. Okay. So what happened when I added feedback? What happened to the bandwidth?
Increased it?
It increased it. It got wider. So when you add feedback, the bandwidth gets wider, and as an appropriate name, you call this wide banding. Wide banding your amplifier. So by dropping the gain, you actually get an increase in your bandwidth. And I don't have, since my display is doing my weird thing where all of your pictures are popped off the side of the display and I can't get you back. I don't know how to ask this then. I should do a poll or something, but for those of you that haven't seen the gain bandwidth video, let me talk about that for a second. There's something very interesting that goes on this line right here, and that is if I take this point, it's at some frequency, we'll call it F1, and this is the value on the y-axis is 20 log of some gain. But if you solve for that gain, for the actual gain, or it's 20 log of gain. But if you you solve and figure out what gain is, turns out that if you take, let's call this 20 log of gain 1, turns out that F1 times G1, well, we'll just say it equals something, some value. Turns out if you take a different gain, so this is really a mess, I'm sorry, 20 log of G2, we'll call this F2. Turns out that any point on this line, if you multiply the frequency times the gain, you'll get that same value. So the gain times the bandwidth So I wrote frequency here, but it's the bandwidth. Gain times the bandwidth, that actually equals a constant all the way along that line. So in the video, I gave you an example with numbers, and I might point you to that if you need gain bandwidth information. But as long as that second pole, remember if we have a 3-stage op amp, we have 2 poles. As long as that second pole's far enough out, after that first pole, any point on this line, so if this is gain 3 and F3, you multiply those two, it will equal the same value. And that value is called gain bandwidth product, or gain bandwidth. You'll see it written both ways, just GBW or GBWP. And the reason why you see that on data sheets is if you know the gain you want, let's say you know the gain bandwidth equals 100 kilohertz. Sorry, this is not very organized, is it, today? Gain bandwidth product. Let's say it equals 100 kilohertz or 100K. And you know you want a gain of 1,000. So let's say the data sheet gives you a gain bandwidth product of 100K, and you know you're designing for a specific application, and you know for that application your boss told you it has to have a, what did I say, a gain of 1,000? Let's say your boss tells you it has to have a gain of 1,000. Then you know that your bandwidth, you'll have that gain only out to 100, because 1K times 100 has to equal the gain bandwidth. So for whatever gain you're targeting, you can figure out the bandwidth. Or if you have a bandwidth, you can figure out what gain you can have on your op amp. So that's why this is a pretty useful metric to have on a data sheet. Okay. Questions on gain bandwidth product? And you can see that if you want a higher gain, your band, if you want a higher gain, your frequency, your bandwidth is smaller, and the trade-off's the other way too. And one of the first questions in 409, if you take Prodnoff, is, I need something out here. You have any ideas how you might get out there? I have these op amps, and this is the underlying magnitude plot of my op amps, but I need a gain and a frequency right here.
Increase bandwidth.
If you can't mess with the op amp, but you have a pile of them in front of you.
Can you add a 0 to the mix?
You can gain cascade, right? Where you have only like a low gain per op amp stage, but since your gain bandwidth is still pretty high for each, you can just kind of like cascade. If you want 1,000 gain, you could do a 10 into a 10 into a 10, and it retains the bandwidth.
Yes. So what happens with that is your starting gain. If you cascade 2, your starting gain is higher. Your pole will be in the same place, but you'll start going down over here. So if you cascade 2 amplifiers, you'll start at a higher gain. You'll still go down. But because you're starting at a higher gain, that line will be out here someplace. So cascading op amps can give you a better gain bandwidth product, or allows you to operate at points you can't with a single op amp. Okay, so that's the answer to one of the homework problems in your first week, 409. If you remember that through the summer, I'll be impressed. Okay, so that's vocabulary seen here. Gain bandwidth product is an important metric. Widebanding is another vocabulary word that's good to know, and bandwidth. So let's see what we've got checked off here. None of them. so, so not doing very well on my list, but let's see. So what's next here? Okay, so first thing that feedback does is it drops your gain, but that actually improves your frequency. Okay, let's just look at basic vocabulary. No, let's look at basic vocabulary here. So let me do one more. I thought I was so organized today, and I'm just not being organized. Let's look at let's finish some more vocabulary since we're doing vocabulary here. For those of you that have had 302, this possibly should look familiar. So does this look familiar from, I can't see anybody, so even if I ask, I can't tell if you're raising your hand, but this is kind of the most basic model of an op-amp there is, op-amp with feedback. And when you have an actual op-amp, the thing that gets multiplied is the difference between the non-inverting input and the inverting input. It's actually the difference between them. So V out actually equals VI plus minus VI minus times whatever the gain of your op-amp is. Okay, so what's happening here is you take the difference of that and multiply it by some number. And that's exactly what this model is here. This circle right here takes the difference between V in, in this case, the V in would be on this terminal, and it takes the difference between V in and whatever is fed back. And then that is amplified and gives you V out, which is exactly what your op-amp's doing. This is just breaking it into pieces, which helps make some of the derivations and work easier. So let's look at this. This feedback block actually takes whatever voltage is on its input, multiplies it by F, and that's the output of the block. So this right here is actually F V out. And then, since that gets subtracted from V in, the voltage at this node is actually V in minus this thing. And then the output of this amplifier right here is this times AV. So what you get is, should I write the whole thing out here? AV times V in minus F V out. So V out equals this whole thing. If you follow it all the way around the loop, if you follow it around the loop, you see that the voltage at this node is this thing, but you also know, because that's where you started, this node is V out. So we can set V out equal to AV V in minus F V out. If you move the V outs over to one side, you get V out, and this is a minus over here, so it turns positive. AV F V out. The only thing left on the right side is the V in term, so that's AV V in. And you can factor V out from here, which gives you a 1 plus AVF equals AVV in. But you want gain, and gain is V out over V in. So what you want to get is, on one side, you want V out over V in equals something. So I'm going to divide both sides by this 1 plus AVF and AV. And that gives you, if you divide both sides by AV, or VN cancels out over here, and then you get AV over 1 plus AVF. And if remember with ideal op amps, what's your gain of an ideal op amp?
It's infinite, right?
Yes. So if AV goes to infinity, what's this equal?
One.
Is it 1 over the frequency?
1 over the frequency, yes. So this becomes very large, much larger than 1, so you can ignore the 1. And now you have AV over AVF, cancel out the AVs and you get 1 over F. And that's the power of an op amp. That's why the feedback, this feedback block right here, it 100% determines the gain of your amplifier system. And that's easy to control, whereas so far, when you've created an op amp, it has a gain of either 900 or 12,000 with just a little change in the circuit. So it's very hard to control just the op amp on its own, but if you hook it up with feedback and make AV really large as you can, doesn't matter whether the gain is linear or what, as long as it's big. This holds true, and the gain of your op amp with feedback is approximately 1 over F. Okay. So in this equation, we have a bunch of values that also have vocabulary. And if you're going to interview with a company that has anything where they might be asking you about op amps, it's good to memorize these terms. And possibly for 409, I'm actually not sure who's teaching it all. We had a great person that we were trying to hire, and the dean's office took so long to get the paperwork back to us. She signed a contract with another university. She signed it on Monday. We gave her the offer on Tuesday. So we just lost another great candidate. But she was going to be teaching it. All right, so vocabulary, lots of vocabulary here. So there is loop gain. If you look at this, if you come for the input of the gain stage and come all the way around, but just don't connect the feedback, just go through all the blocks that give you gain. So the amplifier gives you gain and the feedback block gives you gain. The feedback block gives you a gain less than 1, but it's still gain. If you go around this loop, and if you cascade 2 things with gain, you multiply their gains. So the loop gain is AVF. And because you see it so much, they said, we get tired of writing AVF every time, so let's just call that T. It shows up magically in so many places. Okay, so that is the loop gain. There's the open loop gain. And that is just the gain of your amplifier. It says if I change V in, if I don't connect up the feedback, but I change V in, how much does V out change? And in this picture, you can see that's just the gain of your amplifier. So that's the open loop gain. The closed loop gain is when you connect up the feedback. And since it's the entire system, that's considered a capital AV. And the last term is the feedback factor. My textbook called it the feedback factor, and that's just F. So in all of these equations here, you can identify these different values. You've got that here. You've got this showing up in lots of places. It's a gain of your underlying op amp. The complete gain is actually, I should write it here, is this V out over V in, considering taking the feedback block into account. And then the F is your feedback factor. So all of those terms showing up in this kind of diagrammatic representation of your op amp. So that's terminology. So we've got, see what we've got here. We've got loop gain, open feedback factor. So we've got vocabulary and basics. It's kind of like diff pairs where there was so much vocabulary and they're just things to memorize. Unfortunately, this is kind of the same thing. But if you're having a conversation with somebody about a feedback system with an op amp in it, these terms will help the conversation go smoothly. All right, up to here, I know this has just been listing of vocabulary. Any questions here? Okay. So next on the list, notice that this feedback right here is subtracted from your V in. So it's, unless this is negative, assuming this is positive, the difference, the voltage at this node is going to be less than V in. You're subtracting a value from V in, so this node should be less than V in. Okay. And that's the kind of the definition of negative feedback. When V in moves a certain amount, this feedback comes in here and subtracts from it and makes that difference, keeps that difference under control. Right. Positive feedback is when you change V in and the feedback makes the difference between V in and the feedback, that difference between those two values is bigger. Now, that's positive feedback, okay? When it makes the difference bigger. And then now that bigger thing goes through the amplifier and comes back even bigger, and you start oscillating. With negative feedback, you change this, it makes it smaller. It keeps the difference under control. Okay. Barkhausens we talked about last time, but let's go through it. So let's see, how long is this last stretch here? Let me, no, I need to name it before that. Okay. Yeah, let me go on to Barkhausens real quick because of its importance. So the rule is that for any of the configurations you've seen in 2.11 and possibly other classes, you need negative feedback. Without negative feedback, the system goes out of control and starts oscillating or just rails, goes to VDD or ground. Negative feedback is important. Now, when we're talking about the 3-stage op amp, there's a pole between each stage. So between the input stage and the gain stage, there's a pole. And between the gain stage and the output stage, there's a pole. So there's 2 poles. Let's draw that up. Just going to kind of restate Barkhausens and give you an opportunity to ask a question. Ask questions. Okay, so you have a first pole, and you have a second pole, and it starts going down, negative 20 dB. This is 20 of whatever your gain is per decade. And just one more time on what happens when there's a pole to the phase. Said it a number of times here, but if you have an AC coupling capacitor, you have a low frequency 0. And so the phase actually, the gain is actually coming up. We're assuming there's no AC coupling capacitor. With an AC coupling capacitor, DC won't go through it, so at low frequencies, you don't even see your input. So that's why it's a 0 at a low frequency. But we're assuming no AC coupling capacitor, that we start at 0 degrees phase shift. And your phase starts to go down a decade before your pole and stops a decade after. So not very well drawn here, but. So it loses 45 degrees before the pole and 45 degrees after the pole. And after the first pole, you're down 90 degrees. And after the second pole, you're down 180 degrees. Okay, up to there, any questions on the drawing? Again, I can't see anybody's faces or hands or anything, so just yell out. Okay, good up to there. All right, so when you have a signal, let's say this is the signal getting fed back. If you have 180 degrees phase shift, it actually flips. And if this is negative feedback, then at 180 degrees phase shift, this will be positive feedback. And remember, all of the configurations you've seen before require negative feedback. But with these two phase shifts, now you're getting positive feedback. The rule for Barkhausens is if you draw a line up, let's call this 0 dB. If you draw a line up from the 180 degree phase shift point and you get a gain greater than 0 dB, so you see is the gain greater than 0 dB at 180 degree phase shift. And if it is, this circuit is probably not going to work. Okay. So again, if at 180 degrees phase shift, that signal that's coming back around, if it's greater than 0 dB, the signal that's getting fed back is greater than the input signal. It's actually going to, if it's bigger than the input signal, it's going to override it pretty much in a way. That's not a good way to say it, but okay. But if when you draw the line up, it's less than 0 dB, then there's a good chance that because the signal getting fed back is less than your input signal, there's a good chance that your circuit's going to work. So more vocabulary, but let's look at the poles first. So here's what's called your dominant pole. It's the dominant pole by definition is just the lowest frequency pole. And then there's a secondary pole. And that's just the second lowest frequency pole. So once again, just because it's on the homework, how this circuit right here, it's, I'll put squares around vocabulary. This right here is what's called an unstable system. So when it violates Barkhausen's rule, so Barkhausen's, this is Barkhausen's. Too many vocabulary words. Barkhausen. This is Barkhausen's criteria. That if the gain's greater than 0 dB at 180 degrees phase shift, you're probably in trouble. If it's less than 0 dB at 180 degrees phase shift, you're probably okay. So that's Barkhausen's criteria. So this right here, is this violating Barkhausen's or is it satisfying Barkhausen's criteria?
Violating.
violating because it's greater than 0 dB. So the question is, how do you make it so it's not violating Barkhausen's criteria? Remember, these are from your circuit.
Can you shift the dominant pole to the left?
Yes. So that's the pole that you always target. You want to shift the dominant pole to the left. And how would you do that? How would you do that? What determines the pole?
The resistance and the capacitance you calculated. So you could probably just increase that resistance somehow.
Mhm.
Capacitance in some way.
Yes. Yeah, it turns out changing the resistance is really tough. I mean, you can change the current through your circuit or something like that. It's much easier to increase the capacitance. So in general, if you violate Barkhausen's, what you want to do is move the dominant pole left, and the way to do it is increase capacitance. It's very hard to change the resistance here, but you can. It's easier to add capacitance to your circuit. Okay, so let's see what happens if I move the pole over to here. Then the magnitude starts to drop earlier. The second pole, the secondary pole, you haven't moved yet. So it stays where it is. And now we're satisfying Barkhausen's criteria. So if you're violating Barkhausen's criteria, shift the dominant pole left by adding capacitance. Okay, questions there? Okay, so let's do we'll save the series shunt stuff for next lecture because it works well with loading from the feedback. But let's see. Let's look at an example here, and I'll try to draw really fast. And I'm doing BJTs again just because that's what I started drawing, but exact same arguments for MOSFETs. And let's do, I'll make them all NPNs. And let's call this V2, V1, and Vin, and Vin. So the non-inverting input, when it goes up, V out should also go up. So which one of these is the non-inverting input? Let's give this a try. Let's raise this one. If this goes up, what happens to V1? Does it go up or down?
It goes down.
Goes down. You can think of this just as a common emitter here. Two common emitters kind of stuck together. So common emitters are inverting. So this goes down. All right, then it hits this stage. What happens to V2? Does it go up or down?
It goes up.
Goes up because this is another common emitter. It's inverting. So the input's going down for the common emitter. So the output of the common emitter has to go up. Okay, this is a common collector. Is it inverting?
No.
No.
Oh, so this output also goes up. So you can see if I raise this input, the output goes up. So this has to be the non-inverting input, and this is the inverting input. I think some people in other labs were trying to figure out why their voltage follower wasn't working, and that could be that they just have the inverting and non-inverting input switched, and it's often hard to see with a bunch of stuff stuck in the middle here. So that's always a good test. Just take one of your inputs, raise it, and see if the output goes up. And if it does, then that's the non-inverting input. Okay, so I'm going to randomly say this is the dominant pole. And I'll say this is the secondary pole. I'm just telling you this. On the homework, you actually have to do some math on a few of the problems, but I'm just telling you this right now. So if I want to move, if this graph, the black line right here, this line that's violating Barkhausen's, if that is the Bode plot for this circuit right here, I say, oh my goodness, it's violating Barkhausen's. I need to move that dominant pole down. One way I can do it is, what's a good color? Blue, red, green. I can just add a big old capacitor here. And when I've added a capacitor, one more term for you. When you add a capacitor to move the dominant pole left, that capacitor is called a compensation capacitor. And we saw it in some of the professionally designed op amps. There was that random capacitor in there. That's what it was doing. It was moving the dominant pole left so the op amp would be stable when you hooked it up with feedback. Again, if comparator symbol and an op amp symbol, they look exactly the same on paper. But the difference inside is the comparator probably doesn't have a compensation capacitor because it's not made to hook up with feedback.
You know, I have a question.
Okay.
So in our lab circuit, you actually connected that capacitor on what you called stage 2 between the input and gain stage you connected it between, I think, the in of, I think it was a Darlington pair actually, but would it be different? Could you do it a similar way in this circuit or?
Exactly.
Yeah.
So so this is just fine to put your compensation capacitor there, but why might you want to put it here? Why might it be better to put it from the input of your gain stage to the output of your gain stage instead of just to ground?
Is it because the perceived capacitance is larger because you have that inverting stage, so you can use a smaller capacitor like on the die?
Exactly, yes. So capacitors are gigantic. On the integrated circuit process that we're using right now for a micrometer, for a square micrometer, that's like 7 attofarads. Do you remember attofarads? Anybody know what an attofarad is?
Is it -15?
I think it's
negative 12?
I think it's 18. I'm not sure. I should go back and look that up before I ask questions, right? But yeah, I think it's -18. So for 1 micrometer, you get a few attofarads of capacitance. So you can imagine the way you make a bigger capacitor on an integrated circuit is you increase that area. And however much you've increased this area, so if this is 1 micrometer by 1 micrometer, if you want to double the capacitance, just double one of these and now you have twice the capacitance. But you can imagine if you can't make a microfarad capacitor on a chip. So capacitors are gigantic. So if you can somehow use a smaller capacitor but make it look bigger, then it's great. It frees up a bunch of area on your chip for other things. So in general, compensation capacitors don't go to ground. They go from, if you have a gain stage, you can look at it as a gain stage. And the capacitances go from the input of the gain stage to the output of the gain stage. And now that capacitance looks big on this side. It gets multiplied by your 1 plus AV. On this side, it looks pretty small. It just looks like whatever capacitance you put there. Okay. And so this, what's the effect you're using? when you put a capacitor across a gain stage or across an amplifier to make it look big.
The Miller
Is it the
effect?
Miller effect?
Exactly. So this is using Miller effect. And that's why every pretty much every op-amp, off-the-shelf op-amp I've seen doesn't have capacitance to ground, it has capacitance across a gain stage, just to make the chip smaller. Okay, Miller effect. So that's pretty much everything I think you need to know about stability. Oh, didn't write stability down. Okay, so when it violates Barkhausen's, you say it's unstable. Yeah. So when it violates Barkhausen's, you call it unstable. Now, all the words that I circled in red, those are pretty much the vocabulary you need for discussing, I guess, op-amps and feedback. So any questions on anything that went on here? And Barkhausen's only matters when you're talking about feedback. So everything we talked about today is about feedback. You don't care about this if you're not using feedback, because you're not sending a signal back to your input and messing up your amplifier. If you're not sending a signal back, you don't care about Barkhausen's at all. Okay, that's good. Then the next time we'll just look at how the feedback, so that block with the F in it, how that actually loads your amplifier and decreases your gain. And that's all I got. Any questions? Kind of a rush. I didn't think it was going to feel like this much of a rush, but it was a rush today. Speed lecture. And this is pretty much this information. If you carry this on into future classes, this is what you need. The loading by the feedback block is not often talked about, but it can show up in designing of op-amps, so I wanted to talk about it. Okay, good. Okay, that's what I got for today.
Thank you.
Good luck in your finals.
Thank you.
Thank you, Professor.
All right.
Thank you.
Thanks, Professor.
Bye.
Professor.
Bye. I'm going to take the headset off just to give my ears a break, but I'll look for if people are talking.
Thanks, Professor.
Did somebody say something? Might have been somebody leaving.
Someone just said thanks.
Oh. Hi. I'm thinking about helmeting it today. You don't care about my fashion, do you? Have to take the dog treats out of the helmet, the seaweed out of the helmet. There, we got a helmet.
I respect the fashion statement. When I used to play video games a lot, I had a similar headset, and it
Okay.
made my head hurt a lot. So
Mm.
I understand.
Oh, that must have been loud on your ears, so I'm sorry. I look pretty silly.
I think that the